Welcome Regents students. The topic of today's video is nuclear physics. But I've decided to split the topic into two videos because I felt it was a little too long for one video. There's too much information. First thing we're going to go over is the notation of how you write an element and indicate what's inside the nucleus. So let's take like a variable x, just any element. This of course could be C for carbon or H for hydrogen. So you write the symbol and then you write numbers around it. So the most important number in terms of identifying the element is right here, Z. Z is the number of protons in the atom. So if we had 2 here, that would mean there are 2 protons inside the atom. It's called the atomic number. Not necessary to remember that, the name of it, but you do need to know that that's the number of protons inside. Then letter A is the total number of protons and neutrons together inside the nucleus. So sometimes it's called the mass number, sometimes the nucleon number, sometimes the baryon number, because remember we learned in the previous modern video that protons and neutrons are baryons in the Standard Model. And over here on the right, lower right, is the number of neutrons. It's frequently omitted because you can find the number of neutrons by just subtracting these two numbers. So very often that number is not there. As an example, let's take carbon-14. And so there's 6 here. That indicates there's 6 protons inside the carbon. Otherwise, if there wasn't a 6 here, it wouldn't be carbon, right? The number of protons is what identifies an element as what it is. And then if I wanted to know the number of neutrons, I just take these two numbers and subtract them and I get 8. Of course, we could have had an 8 here to complete the picture, and that would save us that subtraction, but you could just figure it out like that. Okay, so the other thing we're going to talk about are types of nuclear reactions. The two types we're going to talk about today is one is called fission, okay? Fission is when an atom, or nucleus I should say, falls apart. And here's the key thing. When we were learning in chemistry, all the reactions were involving the outside of the, in chemical reactions, the outside, the transfer of the electrons, the movement of electrons between atoms was chemical reactions. Now we're looking at changing the nucleus inside of an atom. So the nucleus of one atom splits into maybe 2 or 3 or 4 parts. It just breaks into smaller pieces. Okay, and here's one example. We've got neutron, which again has 0 protons but 1 nucleon. So that's how we write a neutron. And then uranium, which has 92 protons and in this case a total of 235 nucleons. It breaks into baryon and krypton. Okay, and then here's the atomic number, and then the mass number, and same thing here, and then 3 neutrons. Okay, so there it is. Primarily one big atom breaking into these pieces. Okay, now this is the important. This example not so important because we have zillions of kinds of reactions that can happen, but all of them, 3 things are true. The baryon number is conserved. The baryon number, again, is the total number of protons and neutrons together. So you see here we've got 1 and 235 before. And then after we've got 141 in this atom, 92 in this atom, and then 3 neutrons, so 3 times 1. If you add up, you got 236 on this side, and then here you add these up, you'd get 236 also. So the baryon number is conserved. The other thing that's conserved is the charge in a nuclear reaction. Neutrons before had no charge, but this uranium had 92 protons. This atom had 56 protons, this one 36, and then the neutrons have 0 charge because they're neutral. So if I add up all the charge, I get positive 92 over here and positive 92 over here because this is 0 charge. So charge is conserved. But here's the thing, interesting thing. Energy is not conserved and mass is not conserved. What's conserved is mass energy. Okay? So something interesting. You might be saying, I thought energy cannot be created, destroyed, and mass is always conserved in a chemical reaction. It turns out it is not. And I will explain more about that in the next video, Modern 6A Nuclear 2. But right now, fission reaction, one nucleus breaks into pieces. The other type of nuclear reaction, a fusion reaction, where several nuclei join together and combine. So this is breaking apart, this is joining together. Here's an example. We've got two hydrogen atoms. They smash together and they combine into one thing and they form a helium atom. Why? Now inside, one proton from this hydrogen, one proton from this hydrogen means inside we have two protons. What's an element with two protons? Helium. And we have one neutron inside also. And then this is a gamma photon also produced, energy released. Okay? And I just want to point out that these 1 through 3 are also true for this type of reaction. Okay? So, two types of reaction. This I highlighted as the important thing, not necessarily the specifics of the reaction. Okay, so nuclear reactions are happening all the time. You might be saying, geez, if I don't want to be around any nuclear reactions because there's radiation. Well, then you can't be around anything. This wood under this paper is radioactive. Okay, everything, your body's radioactive. Okay, so why then is it not dangerous to be around this paper? Well, different things decay at different rates. And to model that, we have a concept called half-life. Half-life, capital T, is the time for half of a sample to decay to products. And that for many things is very slow. So like this paper has carbon-14 in it, which I mentioned earlier. Okay, it decays and it's radioactive. Every single living thing has radioactive carbon in it, your body as well. Okay, so stand next to a person, it's radioactive. Okay, the person. And it's a natural thing, so, it's not from pollution or anything. Things living, millions of years ago had the same radioactive carbon in them. So what happens is that carbon, half of it decays every number of years. Turns out for carbon, it's like over 5,000 years. And so when that time increment passes, whatever it is, for carbon 5,000 something years, for certain other, like uranium, it might be 4 billion years. Every 4 billion years, every time a half-life goes by, the amount of substance drops to a half of its original. And then another half-life goes by, we lose, and we go drop another half. Another half-life goes by, we drop another half. Another half-life. So you're always dropping by half, decreasing the amount of substance there. This formula, you can plug in how much you started with. By the way, you can use grams here, moles, whatever you'd like. And then you multiply by 1/2 over this to the power of this fraction, the time that's elapsed over the time to the half-life. This formula, don't use it, don't remember it. The way to solve half-life problems on the Regents Curriculum is simply through division, like in this following example. Let's suppose a lab acquires 12 moles of a radioactive sample with a half-life of 5,000 years. How much will be left in 25,000 years? So, if you wanted to, you can use the formula. So we would say we've got 12 moles times 1/2, I'll put 0.5, raised to the 25,000 years has gone by. Oops, I need parentheses. 25,000 years divided by the time of a half-life, 5,000. And I hit enter and I get the answer. That much is left, 0.375 moles out of the original 12. So you could use the formula, but just one more thing to remember. The easier way to solve this is to just make a table. In one column, I'm going to put time in kilo years, in other words, in 1,000-year increments, and over here, moles. So in the beginning, at time 0, I had 12 moles. 5,000 years later, I am going to decrease half the amount of substance. Another 5,000 years goes by. I decrease another half. Another 5,000 years, I decrease another half. Another 5,000 years, I decrease another half. And then I decrease in another 5,000 years by half again. And there's my answer. So yes, in the Regents, the problems are all of this nature, where you're simply just dividing by half the right number of times to get how much is left. Okay. This, as I mentioned, there's carbon-14 radioactive in us. It can be used, you've heard of carbon dating, to date something. So let's suppose there was a human that was living over 10,000 years ago, and they were eating food, carrots, whatever, bison, and that food is radioactive just like all living things. So they're taking in the radioactive carbon. When they die, they don't eat anymore, right? So that carbon's trapped in their body, and it's decaying over time like this. And when you discover those bones or any material of the living thing that's left, you can measure how much radioactive carbon is left, and then you could say, oh, wait a minute, we have 1/8 of the original. That means 3 half-life years have gone by, 3 half-lives have gone by, so you could take 5,000, whatever the half-life of carbon is, and multiply it by 3, and you find how long ago that thing was living. So that's the concept of a half-life. Okay. However, reactions can be sped up. So you can create chain reactions. The reaction rate can be increased by increasing the concentration of the material. Why is that the case? You take a bunch of radioactive stuff and you concentrate it together, and then when one particle decays, it ejects radiation out of it, and that radiation hits other nuclei and causes them to react. That's what happens in a nuclear bomb. You have uranium that, in the oldest type of bomb, it's exploded inward, and when it reaches a certain density, the chain reaction increases so fast it turns into an explosion. So even though uranium has a very long half-life, you slam it in like that, and now all of a sudden it creates an explosion. In nuclear reactors that make electricity, you're not making it that dense, but you have all these rods, well, maybe like I could have these pencils here, rods of radioactive uranium, and then the closer you put them together, the faster the reaction rate goes. The further you put them apart, the slower the reaction rate goes. So you can control how fast. Put them too close together, you get a meltdown. Well, actually, it's not really, as far as I know, they don't move the rods. What they do is they put in absorbing rods in between. So if you want this reaction to speed up, you remove this and you let the radiation of the two bounce into each other and heat up. You want to slow them down, you put something in the middle that absorbs it, slows the reaction down. So that's what you're doing. You're constantly keeping a reaction from running away and melting the plant down, but fast enough where you're making heat and energy and electricity. As you know, there's radiation, okay, and radiation's bad, okay, so and it could kill you. There are 3 main types of radiation, okay. One is alpha. What alpha is it's a helium nucleus. So in the standard model, remember we saw helium had 2 protons and 2 neutrons. So that gets shot out like a bullet. And out of all the types of radiation, this is has the most mass and most charge. It's like a cannonball running into your body, so it creates the most damage. But interestingly, since it's the largest, it's also the easiest to stop. You could have alpha radiation, oh, that's going to kill me, and then put a piece of paper to protect yourself. And the paper's completely enough to stop the alpha particle. So you might say, well, then why do I have to worry about it? Because I'm always wearing clothes, and that'll protect me. And it will, unless you ingest the radiation, like you eat it, and then alpha radiate something, you accidentally eat a radioactive substance, and then inside of you it does terrible damage. And also when you breathe it in, even worse. Radon gas You've probably heard that some houses have radon gas in them and they're dangerous to be in, so you got to have filters in the basement of a house, because you breathe this into your lungs and it settles in and it creates alpha decay. It's like little tiny cannonballs hitting the inside of your lungs and just destroying them. Okay, so alpha can be very dangerous if you ingest it. The next kind of radiation is beta. Here's the symbol for beta. And what is just an electron shot out of a nucleus? You might be saying, well, how can that happen? How can an electron come out of a nucleus? When essentially a proton turns into a neutron, an electron is ejected. So, a neutron goes into a proton, an electron is ejected. So, but it happens. So an electron comes out of the nucleus. This is less damage compared to alpha, but it's harder to stop. But still, because it's smaller, right? So it's harder, it can go through paper. But a few sheets of aluminum foil are sufficient to stop beta radiation. So still pretty easy to protect yourself from beta radiation. Gamma is the third. What it is a photon. Remember from the electromagnetic spectrum. Let's see. Right? We've got visible light here, ultraviolet, X-ray. Gamma rays are the highest frequency in this whole spectrum, and from E equals HF, they have the most energy. Remember I said a photon's like a little tiny submicroscopic bullet flying, and it can do damage. It can hit your DNA and damage it. So a gamma is a photon. This causes the least damage compared to alpha. It's possible the gamma could go right through your body and not hurt you at all. Of course, it might hit something and hurt you, but it's possible to go through you without causing damage. But the thing that makes it the most dangerous is the hardest to stop, because it has zero charge. So as it's tunneling through atoms made of protons and electrons, it doesn't interact with them. It can go through inches of lead. Okay, so that's pretty scary. You could have maybe a block of lead in front of you to try and protect you, and the radiation is going right through it into your body. Okay, so hardest to stop. So that's it for today. I just want to again review what we talked about today. Okay, so we started with nuclear physics and know how to decipher this notation. This is how many protons. This is protons and neutrons together. And then the two types of reaction, fission and fusion. You just need to know fission is when the nucleus breaks apart, fusion when it joins. That's about all you need to know about them. But also you need to know these three things. Okay, what's true, what's conserved, and what's not conserved. And in the next video, we're going to talk about why energy is not conserved and mass is not conserved. And then half-life, you need to just do these basic calculations. That's why I highlighted this here. Okay, and then a little bit about, types of radiation, but this is probably most likely to be on a typical Regents test and some of these concepts. All right, so that's Nuclear Physics 1. I'll see you in the next video.